All right. Hey guys. I think what we're going to try and do here, because we've got to cover 12.5, 12.6, and 12.7. I think what we're going to try and do is I'm going to try and do 3 different videos, one for each section. That keeps the videos a little bit shorter, and it's also going to help me because it's a really long time to download these things um, if they're larger files. So I'm going to try and do it that way. So we're going to start off with let's see. We're going to start off with, that's ugly, 12.5. See if I can get this right here. There we go. All right, 12.5. We are talking about logarithmic functions. All right, so what I will tell you is that this should pretty much be like what we do in class. As far as, when I put the notes up on the board, the only difference is obviously you won't be able to ask questions, so I'm going to try and go through them. Again, you have the ability to pause, rewind, fast forward, whatever you need to do. Go back and look at things, slow things down if you need time to copy it down. But I would definitely take notes just like we do in class. All right, so logarithmic functions. So you may have heard of these before in the past. And what I really want to get across to you guys here is that a lot of people have a really difficult time with logs. Um, I'm hopefully going to try and make this a little bit easier for you. The biggest thing that you have to understand is that a log is really just a fancy way of writing an exponent. So we're going to say this: logs, for short, are exponents. That's what a log is. If you can keep that in your head, hopefully this won't be too difficult to figure out. All right, so the first thing we're going to talk about is the actual notation for a log, because you have to understand what all the different pieces are. So if we were to write an equation, y equals the log of x base b. And that's the way it's said. This is said the log of x with a base of b. It's read log of x base b. And as you can see here, I am taking the log of x with a base of b. Now, what does this mean? Well, we've already talked about exponentials, and the reason that somebody actually came up with logs is because it's going to make things easier, and it puts exponents in a better form. Um, Logs are actually the inverses of exponentials. So let me show you an exponential equation again. Let's go back to this. X equals b to the y. These two things are inverses of each other. And as we talked about in the earlier sections in chapter 12, one way to figure out if things are inverses is to composite them. So if I were to take and substitute this into x and composite it, or if I was to take this and substitute it into y and composite it and simplify, both would simplify to x, and they would be inverses. Another thing to do is when we get a chance, we'll take a look at the graphs of these, and you can see that they will be inverses because they will be symmetric around the line y equals x. So here are the pieces. If we're going to write a log of x base b, this is the base. And I'll try and explain what the base means a little bit later. Write that a little bit better there. That's a base b. There we go. This piece is what we take the log of. I call this the argument. Some books might call it something different. It is what you are taking the log of. So if you guys have a calculator or, even most phones can do this now, if you were just to type in log 20 or log 13 or something like that and plug that in, it would spit out a number. It's what you're taking the log of. All right, so those are the parts of a log. One of the things we need to be able to do is, because they are inverses, we need to be able to go back and forth between a log and an exponential equation. So that's what we're going to learn how to do first. This is the easiest thing to do, going from a log to an exponential. It's actually a relatively simple pattern. I guess we'll do it in red. Okay. First example. If I were to take the log of 25 with a base of 5 and say that that equals 2. What this is really saying, again, you have to understand that logs are exponents. This whole thing is like having an exponent. And what do I mean by that? Well, let me show you a little pattern here. What this is saying is, think about what I just said. This is the base. 5 is the base. 2, because the whole log, 2, because the whole log is an exponent, is the exponent. So if I took 5 and I raised it to the second power, it should give me the argument. 5 squared equals 25. So if I wanted to rewrite this as an exponential, it would be 5 squared equals 25. So you'll take the base, raise it to the exponent or the answer, and that will give you the argument every time. So the log base 5, 5 raised to the 2 equals 25. I've just changed this from a log to an exponential. Now let's go back up here for a second. Let's look and see if what I just told you actually makes sense. Let's look at this. This is a log, this is the exponential. If I took the base, b, raised it to the answer, that gives me the argument. B to the y equals x. B to the y equals x. These two things are inverses. And this is how you go from a log to an exponential. So we're going to try another one. If I have the log of 1/6 base 6 equals -1. Let's see if this makes any sense. So that means to change this thing into an exponential, because this has to be a true statement that they gave me, it would be 6 to the -1 equals 1/6. 6 to the -1 equals 1/6. And that is a true statement because 6 to the -1 reciprocal, 1 over 6 is 1/6. So we've changed this log into an exponential. Okay, let me extend my page just a little bit here. Okay, let's go with another one. Let's do the log of the square root of 2 base 2 equals 1/2. Again, change this into an exponential. The base raised to the answer gives you the argument. 2 to the 1/2 equals the square root of 2. And of course, that's a true statement. The 1/2 power is a square root. Hopefully you guys are seeing the pattern here is not really that difficult to do. So we'll do log of x base 7 equals 5. Now this one's a little bit different because I have a variable in it. And this is one of the reasons why it's actually important to be able to go from a log to an exponential, and we're going to learn how to go backwards as well. Because if I want to find out the value of x that makes this true, if I want to solve this equation for x, I'm going to need to be able to put this into an exponential. Once again, base raised to the answer gives you the argument. So that would be 7 to the 5th equals x. Now you could obviously plug 7 to the 5th in your calculator. I'm not really worried about the value of that right now, but that would be the answer for x if you had to solve it. But that's writing this log in an exponential form. All right. Kind of hard for me here because I'm so used to asking you guys if you have any questions after stuff like this, but I can't really do that. So hopefully that's good. Now that we know how to go from a log to an exponential, now we're going to learn how to go from an exponential back to a log. So let me just go ahead and extend my page here. Obviously, you guys might have to use another page, and that's fine. All right, so now let's go back to black. Now let's go from exponential form to logs. So let's do 9 to the 3rd equals 729. Yes, that is a true statement. That's what 9 to the 3rd is. But now we want to take this and we want to write this as a log. So if I want to write this as a log, there's no real specific pattern to this one, so it's not quite as easy to see how to do it. But the first thing you're going to do is you're just going to write log, and you have to have a log of something. And that log, whatever we're going to write here, has to equal something. If you remember what I said just a couple minutes ago, a log is an exponent. So what does this whole log have to equal? Well, come over here. What's the exponent? The only exponent is 3. So 3 goes out here. If you're really thinking about it, which one of these has a base? 9 is the base of this in particular problem because 9 is the bottom number which is being raised to some power. So the base, which is this subscript down here, is 9. And what am I taking the log of? That's the argument. That's the thing that's left. 729. So the log of 729 with a base of 9 equals 3. And you can always go back and double check. 9 to the 3rd equals 729. 9 to the 3rd equals 729. Okay, I didn't write the little arrows here, but that's what you would do. All right, let's try another one. We'll try a few more of these. 6 to the negative 2 equals 1/36. So again, we're going to come over here. We're going to write log. And the log has to equal something. The log will equal the exponent. The exponent is negative 2. What's the base? What's the subscript? Well, it's 6, because 6 is the base of this in particular piece right here. What's being raised to a power, and it's of 1/36. Log of 1/36, base 6, equals negative 2. And again, double check. 6 to the negative 2 equals 1/36. 6 to the negative 2 equals 1/36. All right, 5 to the 1/3 equals the cube root of 5. Okay, let's write it as a log. Log has to equal something, equals the exponent. The exponent is 1/3. What am I having as a base? The base is 5. And what am I taking the log of? That would be a cube root of 5. One more. I'm going to throw another symbol in there that we haven't really used a lot. Pi to the 4th power equals x, just to throw some different stuff in there, but nothing changes because it's different. Let's do purple. Log equals, the exponent is 4. That's what a log equals. It's an exponent. The base is pi, so that's my subscript. And the argument has to be x. Pi to the 4th equals x. Pi to the 4th equals x. This pattern holds. All right, so here's why that's important, to be able to go back and forth between these things. So the idea is if we need to solve an equation, sometimes you have to be able to go from a log to an exponential or from an exponential to a log, depending on where the variable is that you're trying to solve for. So let's start off, go back to black. Let's start off with the log of 1/4 base 4 equals x. So if I actually want to find the value of x, I would need to solve this. Now technically x is already solved for because x does equal the log of 1/4 base 4, but that doesn't help us figure out what x would actually equal here as a value. So it might be better to go ahead and put this one into exponential. 4 to the x equals 1/4. 4 to the x equals 1/4. Now again, the idea would be if we can create the same base on both of these, we could probably solve for x pretty easily. Well, remember that 1/4 is the same thing as 4 to the negative 1 power. So this is 4 to the x equals 4 to the negative 1. So if this is the case, since the bases on both sides of the equal sign are exactly the same, the exponents must be the same. If that's the case, then x must equal negative 1. Okay, so I've actually simplified this and found that the value of x here is negative 1. Okay, the location of the x still makes a big difference as to how we're solving it, but it's the same general idea. So let's do another one. Log of x base 5 equals 3. Okay, this one you pretty much have to take this out of log form to solve. So again, we're going to say 5 to the 3 equals x. This one will actually be a little bit easier. 5 to the 3rd equals x. All I have to do now to solve for x is simplify 5 to the 3rd. And this is one of those cubes that you either should know or you have your chart and you should be able to figure out, but that's 125. So x is 125. Okay, let's do a couple more. Let's do log of 1 base 3 equals x. All right, this is actually kind of a special one, but we're still going to go through the process because I want you to see what's happening. 3 to the x equals 1. 3 to the x equals 1. Well, what's the only thing I can raise this 3 to get 1? What's the only power that you can raise something to and get 1 as long as the base is not 1 itself? Anything raised to the 0 is 1. So that means that x must be 0. Anything raised to the 0 is 1. So x must be 0. And the interesting thing about this is it doesn't matter what this base is. This could be 72 to the 0 is 1. This could be 123 to the 0 is 1. This base right here doesn't matter. So ultimately, and we're going to talk about this later, the log of 1 doesn't matter what the base is always going to be 0. So we will talk about that in a second. Let's see how good we are here. So this is the log of 1 base b equals x. Okay, if you got what I just said, this base doesn't matter. I'm taking the log of 1. So b to the x has to equal 1. which means that x must be 0. The log of 1 doesn't matter what the base is, will always be 0. All right. Now let's try, no, actually before we try that, let's go ahead and go through some of the properties. Let me write some of these down for you. Hopefully this makes sense as to why this is, but a lot of times people just go and memorize these properties. I find it easier to just kind of understand why it works, but at the same time, some people just like to memorize, so we're going to write the properties down. So properties of logs. That was awful. Properties of logs. Better. All right, so one of the first properties that you need to know is that the log of 1 doesn't matter what the base is always 0. And again, anything raised to the 0 gives you 1. So if you think about it in terms of an exponential, that makes sense. The log of b to the x base b, well, think about this. B to some power must give me b to the x. B to some power must give you b to the x. Well, this power has to be x. B to the x equals b to the x. So that's the second property. Anytime that this value of the x argument and the base are the same, whatever this exponent is going to be the log. That's the answer. And then the third property, which is one that we're not going to probably use quite as much, is b raised to a log of x base b. So now it's an exponential form, but it has a log in its exponent. Basically, this is compositing a log with an exponential. And if you composite these things, because they're inverses, should give you the argument, which is x. So if you have a base here and then a log with the same base in the exponent, whatever the argument is will be the answer. All right, those are the three properties that I really wanted to go through before we move on to solving exponential equations. I'm sorry, to solving some more log equations. I'm not with it right now. Here we go. Okay, so using those properties, these should be pretty simple. If we take the log of 3 squared base 3, what you should notice is that this one right here is exactly the same as property number 2. The argument and the base are the same. If that's the case, the answer is the exponent. And again, think about it. 3 squared equals 3 squared. Should make perfect sense. So if we have log of 7 to the negative 1 base 7, again, base and argument are the same. The answer is the exponent. Okay, not really that difficult to do. 5 raised to the log of 3 base 5. Base here are the same. The argument is the answer. And one more like that. 2 raised to the log of 6 base 2. Base here are the same. The argument is the answer. Now, these must be the same. This base and this base, this base and this base, they have to be the same. If these are different bases, this property doesn't hold. We have to come up with some other way to solve these. All right, so while we're not going to go into extreme detail, we do need to cover a few things when it comes to the graph of logs. Oh, that's awful. Okay, that's not much better, but it'll work for now. All right, if you remember exponentials, now let's see how well we can do this. Exponentials look like this. And we've been saying that logs and exponentials are inverses of each other, which means they must be symmetric around the line y equals x. So the log, if it's symmetric to this thing, if I folded this over this y equals x line, is going to look something like this. Okay, not perfect, but that's not bad. And remember, the inverses take on the property of their domains and their ranges being switched. So if you go back to the notes that we took on exponentials, the domain of an exponential is all real numbers. Okay, there's no x value that doesn't work here. So the domain of this red one, which is an exponential, is all real numbers, which means that the range, man, got to learn how to write today, which means that the range of a log is the same as the domain of an exponential. So it's all real numbers, or negative infinity to infinity. And the domain of a log should be the same as the range of an exponential. And remember, we talked about the range of this thing being the y values, and this thing never touches y equals 0, so it goes from 0, not including 0, all the way up to infinity. Well, this is going to be the same thing. The only difference is its domain is going to be the x values. The x values here never will touch the y-axis, so it'll never hit 0, but it will go out to infinity. So it's 0 to infinity. And this is your standard log. So this would be the log, the basic log function. Remember that this point right here was the point 0, 1. So this point, because they are switched, will be the point 1, 0. If it's a standard log, this is going to be your x-intercept. Things can be changed if we shift the graphs up, down, left, right, do some other stuff to it. But for a standard log, this is the basics. All right, what's good to know is the domain and the range and how they fit with the exponentials. All right, and while we're not going to go into extreme detail with these graphs, I would like to go through one graph specifically where you can actually just go ahead and graph the whole function. Man, these are just really crooked for some reason today. I'm not drawn straight. All right, so let's say that we are given y equals the log of x base 2. Well, what might be an easier thing to do is to put this into the form of an exponential in order to get our actual values of x and y. So if we write this as an exponential, that's the same thing as 2 to the y equals x. One way or another, we need to create ourselves a little chart here. So x, y. All right, so what we're going to do is we're actually going to pick values of y and figure out the x values in this case, because it's easier to do it that way. So if I start off with an easy one, let's start off with y equals 0. If y is 0, 2 to the 0, anything to the 0 is 1. So once again, that point 1, 0, which is approximately right here, that's the standard point on the log that's going to be our x-intercept. If I were to take y to be 1, 2 to the 1, 2 to the first power is 2. If I were to take y to be 2, 2 squared is 4, so x would be 4. So I've got a few points here. So x is 2, y is 1. It's about right there. X is 4 out here, Y is 2. It's about right there. It's kind of starting to take that shape that we saw above. Let's go backwards. If I were to take Y to be -1. Well, 2 to the -1, remember that makes it a reciprocal. So 2 to the -1 is the same as 1 over 2, so X would be 1/2. And then we'll go one more. If Y is -2, that's now 2 to the -2, which is the same as 1 over 2 squared, which is 1/4. So let's see here. X is 1/2, Y is -1. X is 1/4, Y is -2. And you should be able to see that this graph is starting to take on the general log shape. And it's going to ride up along the y-axis, cross through, trying to keep it there. It's not very smooth, but it's close enough. And there you go. This is the graph of y equals log of x base 2. All right, that finishes up 12.5. We'll come back with a second video for 12.6.